In this lab, we are exploring the concept of constant velocity motion as it pertains to Newton's second law. Newton's second law relates the initial and final velocities of an object in a system using force, time, and the object's mass. The equation is shown here. The final velocity is equal to the initial velocity plus the net force over mass multiplied by the change in time. Taking a look at the units in this equation brings the concept together. Mass cancels mass, and the change in time multiplied by acceleration cancels the seconds, giving an average change in velocity. For the purposes of this lab, we have assumed that the net force on any given object in a system is zero. Therefore, the object will move at a constant velocity motion for the duration of its movement. When the net force is equal to zero, the entire term cancels, leaving the final velocity to be equal to the initial. I have tested this concept using a foam roller. The object was rolled across the floor as such. The only action that was placed on the object was the force by the hand to roll it across the floor. As mentioned before, we are assuming that the net force on our object is zero. While there are definite forces present, we will simply assume that they are not affecting our system. The video was inputted into Tracker, the software that I will use to show how I calculated constant velocity of motion of this object. In Tracker, we can see the setup of the experiment, of which the system only consists of the foam roller. In this lab, we assume the effects of the surroundings, the floor, are negligible, and the blue line is a calibration stick, which allows Tracker to understand the measurements of the video in order to create accurate data. It is a known measurement of an object during one of the frames of the video. This one reads 1.350 E-1, which translates into 13.5 centimeters or 0.135 meters, which is the diameter of the foam roller. The axes are also shown, with the positive x direction pointing to the right and the positive y direction pointing up. The movement of the foam roller in the positive x direction was tracked in the data produced a graph and a table, shown on the right of the screen. The graph in the top right is a displacement versus time graph, with time in seconds on the x-axis and the displacement in meters on the y-axis. As one can see, the data shows the movement of the object to follow a seemingly equidistant path over equal time intervals, which would be conducive with our assumptions of constant velocity motion for Newton's second law. I created a computer model to better picture the concept of constant velocity motion using VPython. I started with the basic code that was given and modified it to fit my experiment. I started with the system properties and initial conditions. I changed the mass to 0.680 as the foam roller weighs 680 grams and the VPython is written in SI units, which would be kilograms. The next thing I did was I changed the initial location. I retrieved that from my Tracker file, which I placed the object relative to the origin that I set. Next, I calculated my initial velocity. Using the formula of change in distance over change in time using the first two data points in my system only in the x direction, which came out to 0.5 meters per second. And like in my Tracker file, time started at 0. Next, I checked my time step, which would be my delta t. I left it at the already 0.1 as it is small enough. Next, I activated the CSV writer in order to get data output that would be able to be compared to my Tracker data. For the calculation loop, I changed my time so that it would stop at the same time my experiment did, 1.72 seconds. Next, I edited the force vector to be a zero vector, as we are assuming the forces on the object in this experiment sum to zero. Next, I set the ball's velocity to be calculated by Newton's second law, using the variables from the assignment statements that were set in the initial conditions. The position vector statement was also rewritten to be calculated using the velocity used in the previous statement. The last line was edited to uncomment the CSV writer so that data could be saved. When run, the program shows a model like this. It then saved a CSV file of all the time versus position data points. My next step is to compare the model with the experimental data. When graphed together, the data looks like this. The red line shows the data produced by the model, while the blue dots show the data produced by the experiment. As one can see, the experimental data does not match up perfectly to the models. The model is higher than the experiment. In the beginning, it is close, but the different slope between the lines is apparent after about 0.4 seconds. This could be due to the fact that the object will inevitably be faster in the first few frames of the video because of the force that was used to push it. Therefore, the model was based off the slightly faster initial velocity of the object. We also assume in the model that there are no forces, but in real-life experiments we cannot assume this. Forces such as friction, gravity, and others all play a role in whether or not an object stays in constant velocity motion.